Hello and welcome to Earth Science, Lecture 6, Metamorphic Rocks and Resources from Rocks. Metamorphism, which means to change form, is a process that leads to changes in the mineralogy, texture, for example grain size, and sometimes chemical compositions of rocks. Metamorphism occurs most often when rock is subjected to a significant increase in temperature and/or pressure. Metamorphic rocks are produced from pre-existing igneous, sedimentary, or even other metamorphic rocks. Thus, every metamorphic rock has a parent rock, that is, the rock from which it was formed. In response to these new conditions, the rock gradually changes until it reaches a state of equilibrium with the new environment. Most metamorphic changes occur at the elevated temperatures and pressures that exist in a zone beginning a few kilometers below the surface, extending all the way down into the Earth's mantle. Metamorphism often progresses incrementally, from slight changes, which is called low-grade metamorphism, to substantial changes, which is called high-grade metamorphism. For example, under low-grade metamorphism, the common sedimentary rock shale will become the more compact metamorphic rock slate. In more extreme environments, however, metamorphism causes a transformation so complete that the identity of the parent rock cannot be determined at all. In high-grade metamorphism, such features as bedding planes, fossils, and vesicles that may have existed in parent rocks are obliterated. Furthermore, when rocks deep in the crust, where the temperatures are high, are subjected to directed pressure, the entire mass may deform, producing a large-scale structure such as folds. Many students are confused by the metamorphic concept that new minerals can crystallize from other minerals in a rock that does not melt. An analogy that may have some reference to many of you is that of clay before it is fired in a kiln. So in this case, we can observe the properties as clay is being heated in a kiln. So before the dry clay is fired, it is soft enough to bend and scratch a name into. It can be torn into chunks and molded. However, after firing the piece, it is very hard and shatters when it is stressed. The clay minerals of that clay have been recrystallized, producing the physical changes in the rock without melting it and resolidifying. By definition, rock undergoing metamorphism remains essentially solid. In the most extreme metamorphic environments, the temperatures approach those which rock melts. However, if appreciable melting occurs, the rocks have entered the realm of igneous activity. Most metamorphism occurs in one of two settings. One, when rock is intruded by magma, which is known as contact metamorphism, we see that the magma heats the adjacent rock to temperatures that cause metamorphic changes. Or two, during mountain building, where great quantities of rock are subjected to pressures and high temperatures associated with large-scale deformation called regional metamorphism. Extensive areas of metamorphic rocks are exposed on every continent. Metamorphic rocks are an important component of many mountain belts, where they make up a large portion of a mountain's crystalline core. Even the stable continental interiors, which are generally covered by sedimentary rocks, are underlain by metamorphic basement rocks. In each of these settings, the metamorphic rocks are usually highly deformed and intruded by igneous masses. Consequently, significant parts of Earth's continental crust are composed of metamorphic and associated igneous rocks. The agents of metamorphism include heat, confining pressure, differential stress, and chemically active fluids. During metamorphism, rocks are often subjected to all four of these agents simultaneously. However, the degree of metamorphism and the contribution of each agent varies greatly from one environment to another. So let's go ahead and step through each of these four agents that lead to metamorphism. The first is heat. Thermal energy, commonly referred to as heat, is the most important factor driving metamorphism. It triggers chemical reactions that result in the recrystallization of existing minerals and the formation of new minerals. Thermal energy for metamorphism comes mainly from two sources. Rocks experience a rise in temperature when they are intruded by magma rising from below, contact metamorphism, In this situation, the adjacent host rock is baked by the emplaced magma. By contrast, rocks that formed at the Earth's surface experience a gradual increase in temperature and pressure as they are taken to greater and greater depth. In the upper crust, this increase in temperature averaged about 25 degrees Celsius per kilometer. When buried to a depth of about 5 miles, where the temperatures are between 150 and 200 degrees Celsius, clay minerals tend to become unstable and begin to recrystallize into others. However, many silicate minerals, particularly those found in crystalline igneous rocks, quartz and feldspar, for example, remain stable at these temperatures. Thus, these minerals require much higher temperatures in order to metamorphose and recrystallize. Pressure, like temperature, increases with depth as the thickness of the overlying rock increases. Buried rocks are subjected to confining pressure. This is similar to water pressure in that forces are equally applied in all directions. The deeper you go in the ocean, the greater the confining pressure. The same is true for buried rock. Confining pressure causes the spaces between mineral grains to close, producing a more compact rock that has a greater density. Further, at great depths, confining pressure may cause minerals to recrystallize into new minerals that display more compact crystalline forms. During episodes of mountain building, large rock bodies become highly crumpled and metamorphosed. Unlike confining pressure, which squeezes rock equally in all directions, the forces that generate mountains are unequal in different directions and are therefore called differential stresses. Rocks subjected to differential stress are shortened in the direction of greatest stress and elongated along the direction perpendicular or in the opposite direction of those stresses. The deformation caused by differential stress plays a major role in developing metamorphic textures. In surface environments where temperatures are relatively low, rocks tend to be brittle, and as a result they fracture when subjected to differential stress. For example, think of a heavy boot crushing a piece of fine crystal. Continued deformation grinds and pulverizes the mineral grains into smaller and smaller fragments. By contrast, however, in high-temperature, high-pressure environments deep inside the Earth's crust, rocks are more ductile and tend to flow rather than break. Think of a heavy boot crushing a soda can. When rocks exhibit ductile behavior, their mineral grains tend to flatten and elongate when subjected to differential stress. This accounts for their ability to generate intricate folds, like you can see in the image in the right. The last type of agent for metamorphism is chemically active fluids. Ion-rich fluids composed mainly of water and other volatiles, that is, materials that readily change to gases at the surface, are believed to play an important role in some types of metamorphism. Fluids that surround mineral grains act as catalysts that promote recrystallization by enhancing ion migration. In progressively hotter environments, these ion-rich fluids become correspondingly more reactive. Chemically active fluids can produce two types of metamorphism. The first type changes the arrangement and shape of the mineral grains within a rock. The second changes the rock's chemical composition. When two mineral grains are squeezed together, the parts of their crystalline structures that touch are the most highly stressed. Atoms at these sites are readily dissolved by the hot fluids and move to fill the voids between individual grains. Thus, hot fluids aid in the recrystallization of mineral grains by dissolving material from regions of high stress and then precipitating or depositing this material in areas of lower stress. As a result, minerals tend to recrystallize and grow longer in a direction perpendicular or opposite to the compressional stresses. When hot fluids circulate freely through rocks, ionic exchange may occur between adjacent rock layers, or ions may migrate great distances before they are finally deposited. The latter situation is particularly common when we consider hot fluids that escape during the crystallization of an intrusive mass of magma. If the rocks surrounding the magma differ markedly in composition from the individual invading fluids, there may be a substantial exchange of ions between the fluids and the host rock. When that occurs, the overall composition of the surrounding rock will change. So, the degree of metamorphism is reflected in a rock's texture and mineralogy. When rocks are subjected to low-grade metamorphism, they become more compact and thus more dense. A common example is the metamorphic rock slate, which forms from shale when it is subjected to temperatures and pressures only slightly greater than those associated with the compaction that lithifies the sediment. In this case, differential stress causes the microscopic clay minerals in shale to align in a more compact arrangement that is found in slate. Under more extreme temperatures and pressures, stress causes certain minerals to recrystallize. In general, recrystallization encourages the growth of larger crystals. Consequently, many metamorphic rocks consist of visible crystals, much like the coarse-grained igneous rocks we talked about previously. The term foliation refers to any nearly flat arrangement of mineral grains or structural features within a rock. Although foliation may occur in some sedimentary and even a few types of igneous rock, it is a fundamental characteristic of regionally metamorphosed rock. That is, rock units that have been strongly deformed mainly during folding. Foliation in metamorphic environments is ultimately driven by compressional stresses that shorten the rock units, causing mineral grains in pre-existing rocks to develop parallel or nearly parallel alignments. Examples of foliation include the parallel alignment of platy, that is flat and disc-like minerals, such as the micas, elongated or flattened pebbles that are characteristic of metaconglomerates, compositional banding, in which dark and light minerals separate, generally generates a layered appearance, and rock cleavage, in which rocks can be easily split into slabs. It is important to note that rock cleavage is not the same as mineral cleavage. Not all metamorphic rock exhibits a foliated texture. Those that do not are referred to as simply non-foliated, and typically develop in environments where deformation is minimal and the parent rocks are composed of minerals that have a relatively simple chemical composition, such as quartz or calcite. For example, when a fine-grained limestone, that is a rock made of calcite, is metamorphosed by the intrusion of a hot magma body, the small calcite grains will recrystallize and form larger interlocking crystals. The resulting rock, marble, exhibits large, equidimensional grains that are randomly oriented, similar to those in coarse-grained igneous rock. So the point is, when you have differential stress, our rocks can be metamorphosed in a process of foliation that basically causes all of the mineral grains to align in a straight direction, up and down in this case. So here is a way to organize or classify our common metamorphic rocks. This table here is mostly a reference for my students in the actual course, where you can look at this and get a better understanding of how all of these are related. In general, though, we can see that our rocks are classified by their texture and whether or not they're foliated. So we can use this to help classify and even identify some of our rocks, like we will in lab if you're in my course. Still, we will take a look at each of these rocks in detail, so we'll spend about a slide on each of the main ones on the left here. So let's begin with the very first one, slate. Slate is a very fine-grained, foliated rock composed of minute mica flakes that are too small to be visible to the unaided eye. A noteworthy characteristic of slate is its excellent rock cleavage, or tendency to break into flat slabs. This property has made slate a useful rock for roof and floor tiling, as well as billiard tables. In fact, the structure you see here of slate is actually very similar to my fireplace. My fireplace looks exactly like this, just with lighter color slate. Slate is usually generated by the low-grade metamorphism of shale. Less frequently, it is produced when volcanic ash is metamorphosed. Slate's color is variable. Black slate contains organic material, red slate gets its color from iron oxides, And green slate is usually composed of chlorite, a greenish mica-like mineral. Next, we can discuss PHYLITE, which represents a degree of metamorphism between slate and schist, the following rock we'll talk about. Its constituent platy materials, mainly muscovite and chlorite, are larger than those in slate, but not large enough to be readily identifiable with the unaided eye. Although PHYLITE appears similar to slate, it can typically be easily distinguished from slate by its glossy sheen and relatively wavy surface. So if you look back and forth, I'm going to go back and forth here, between slate on the bottom and PHYLITE here, they're both platy, they're both relatively dark, but you're mainly looking at the fact that this has a more wavy appearance and is a little bit more glossy. Next is schist. Schists are moderately to strongly foliated rocks formed from regional metamorphism. They are platy and can be readily split into flakes or slabs. Many schists originate from shale parent rock. The term schist describes the texture of a rock regardless of composition. For example, schists composed primarily of muscovite and biotite are called mica schists. So to the right you see two examples of different forms of schist. Next is gneiss. This is the term applied to banded metamorphic rocks in which elongated and granular minerals predominate. The most common mineral in gneiss is quartz and feldspar, with lesser amounts of muscovite, biotite, and hornblende. Gneisses exhibit strong segregation of light and dark silicates, giving them a characteristic banded texture. While still deep below the surface where temperatures and pressures are great, banded gneiss can be deformed into intricate folds, like you can see on the bottom right. And so here's just a great rock joke, because who doesn't love those? Two metamorphic rocks are talking. One says, "Why are you so nice?" And the other says, "Because I am not full of schist." We have fun here. Anyway, next up is marble. Marble is a more coarse, crystalline rock whose parent rock is limestone. Marble is composed of large, interlocking calcite crystals formed from the recrystallization of smaller grains in the parent rock. Because of its color and relative softness, which is a hardness of only 3 on the Mohs scale, marble is a popular building stone. White marble is particularly prized as a stone from which to carve monuments and statues, such as the Lincoln Memorial in D.C. and the Taj Mahal in India. Fairly similar to marble in appearance is quartzite. This is a very hard, metamorphic rock often formed from quartz sandstone. Under moderate to high-grade metamorphism, the quartz grains in sandstone will fuse. Pure quartzite is white, but iron oxide may cause a reddish or pinkish stain, and dark minerals can cause a more gray to green color. Although quartzite can sometimes appear similar to marble, a piece of quartzite will not be able to be scratched by a metal blade, and quartzite will not fizz when in contact with hydrochloric acid. So even though they appear similar in many cases, they can be tested for to differentiate the two. So those are our most common metamorphic rocks. At this point, we're going to sort of shift gears and end our rock discussion on resources that we acquire from rocks, and also taking a look at some energy resources that we've used in the United States. So let's start again with our rock resources. The outer layer of Earth, which we call the crust, is only as thick when compared to the remainder of Earth as a peach skin is to a peach. Yet it is of supreme importance to us. We depend on it for fossil fuels and as a source of such diverse materials as the iron from automobiles, salt for flavoring food, and gold for the world trade. In fact, on occasion, the availability or absence of certain earth materials has altered the course of human history. As the world population grows and the material requirements of modern society increases, the need to locate additional supplies of useful materials becomes more challenging. Most of the energy and mineral resources used by humans are non-renewable. To give you an idea, the annual per capita consumption of several important minerals and resources are shown. These data reflect an individually portrayed share of the materials required by the industry to support the needs of our modern society. So here we can see it's broken down into metallic, non-metallic, and energy resources. We're going to take a little bit closer look at each of these three in the coming slides. Let's begin with the first category, metallic resources. Some of the most important accumulations of metals, including gold, silver, copper, platinum, and nickel, are produced by igneous and metamorphic processes that concentrate desirable materials to the extent that extraction becomes feasible economically. Igneous processes that generate some metal deposits are straightforward. For example, as a large magma body cools, minerals that crystallize early on and are heavy will sink to the lower portion of the chamber. If you recall from a previous lecture, we called this magmatic differentiation. And it's particularly important in large magmas where chromite, an ore of chromium, magnetite, and platinum are occasionally generated. Layers of chromite, along with the other heavy minerals, are mined from such deposits. So the table on the right just shows a series of metals, their ores, and where they can be found. Igneous processes are also important in generating other types of mineral deposits. For example, as a granitic magma cools and crystallizes, the residual melt becomes enriched in rare elements and heavy metals, including gold and silver. Furthermore, because water and other volatile substances do not crystallize along with the bulk of the magma body, these fluids make up a high percentage of the melt during the final phase of solidification. Crystallization in a fluid-rich environment as such enhances the migration of ions and results in the formation of crystals several centimeters or even a few meters in length. The resulting rocks, called pegmatites, are composed of these unusually large crystals. So you can see a person pointing to two large samples of these pegmatites, very large crystals. Most pegmatites are granitic in composition and consist of large crystals of quartz, feldspar, and muscovite. Feldspar is used in the production of ceramics, and muscovite is used for electrical insulation and glitter. Some pegmatites contain semi-precious gems such as beryl, topaz, and tourmaline. Moreover, minerals containing the elements lithium, gold, silver, uranium, and the rare earths are sometimes found. Most pegmatites are located within large igneous masses or as veins that cut through the host rock surrounding a magma chamber. So you can see arrows pointing to this here, pegmatite deposits. Among the most important ore deposits are those generated from hydrothermal solutions. Note, hydra means water, thermal means heat, so hot water solutions. Included in this group are the gold deposits of the Homestake mine in South Dakota, the lead, zinc, and silver ores in Idaho, and the silver deposits of the Comstock lode in Nevada, and the copper ores of the Keweenaw Peninsula in Michigan. Anyway, the majority of hydrothermal deposits originate from hot, metal-rich fluids that are associated with cooling magma bodies. During solidification, liquids plus various metallic ions accumulate near the top of the magma chamber. Because these hot fluids are very mobile, they can migrate great distances through the surrounding host rock before they are eventually deposited. Some of this fluid moves along fractures or bedding planes, where it can cool and precipitate the metallic ions and produce vein deposits. Many of the most productive deposits of gold, silver, and mercury occur as hydrothermal vein deposits that you can see here in the figure, basically looking like red tree branches. But another important type of accumulation generated by hydrothermal activity is called disseminated deposits. Rather than being concentrated in narrow veins, these ores are distributed as minute masses throughout the entire rock mass. Much of the world's copper is extracted from these disseminated deposits, including the huge Bingham Canyon copper mine in Utah. Because these accumulations contain only 0.4 to 0.8% of copper, percent copper, between 125 and 250 metric tons of ore must be mined for every ton of metal recovered. The environmental impact of these large excavations, including the problems of waste disposal, is significant. Next, we can discuss non-metallic mineral resources. Earth materials that are not used as fuels or processed for the metals that they contain are referred to as non-metallic mineral resources. Non-metallic mineral resources are extracted and processed either to make use of the non-metallic elements they contain or for the physical and chemical properties they possess. Although these resources have diverse origins, many are sediments or sedimentary rocks. Because a large percentage of these materials are used in manufacturing to make fertilizer, processes that we rarely see, their importance is easy to underestimate. The quantities of non-metallic minerals used each year are enormous. For example, per capita consumption of non-fuel resources in the United States alone is nearly 11 metric tons, of which more than 94% are non-metallics. Non-metallic mineral resources are commonly divided into two broad groups: building materials and industrial minerals. Limestone, for example, which is a rock formed from the mineral calcite, is perhaps the most versatile and widely used rock of all. As a building material, it is used not only as crushed rock in building stone, but also in making cement. As an industrial mineral, limestone is an ingredient in the manufacturing of steel and is used in agriculture to neutralize acid soils. Building materials are also include cut stone, aggregate, which is sand, gravel, and crushed rock, gypsum for plaster and wallboard, clay for tile and bricks, and cement, which is made from limestone and shale. Cement and aggregate go into the making of concrete, a material that is essential to practically all construction. A wide variety of resources are classified as industrial minerals. Some are sources of elements or compounds used in the manufacturing of chemicals. Others, including fluorite and limestone, are parts of the steelmaking process. Corundum and garnet are used as abrasives, and so we can see fertilizers being made from this as well, from sylvite, for example. Deposits of industrial minerals are generally far less common than those of building materials. So let's focus on a few important energy resources. Earth's tremendous industrialization over the past 2 centuries has been, and continues to be, fueled by the burning of coal, petroleum, and natural gas. About 81% of the energy consumed in the United States today comes from these 3 basic sources. Our reliance on fossil fuels is obvious. Although we are increasing the quantities of energy from alternative resources such as solar, wind, geothermal, and hydroelectric, the United States Department of Energy projects that fossil fuels will remain a primary source of energy for decades to come. In addition to oil and natural gas, coal is commonly called a fossil fuel. This designation is actually appropriate because when coal is burned, energy from the sun that was stored in plants many millions of years ago is being used, so hence the actual burning of fossils. In the United States, coal fields are widespread and contain supplies that should last for hundreds of years. Based on U.S. coal production in 2015 of about 0.9 billion short tons, the United States estimated that recoverable coal reserves would last for about another 283 years. But note, that's just based on the ones that we know of. We could find more. So there's a time limit, right? Coal is non-renewable, and as far as we know, it will last for about 283 more years. Coal is plentiful, but its recovery and use present a number of challenges. Surface mining, which is costly, can turn the countryside into a scarred wasteland if careful reclamation is not carried out to restore the land. Currently, all U.S. surface mines are required to reclaim their land, however. Although underground mining does not scar the landscape in the same degree, it has been costly in terms of human life and health. Strong federal safety regulations have made U.S. mining quite safe. However, collapsing roofs, gas explosions, and the required heavy equipment remain hazardous. In addition, burning coal produces emissions that adversely influence the environment and human health. Principal emissions resulting from coal combustion include the following: sulfur dioxide, which contributes to acid rain and respiratory illness; nitrogen oxides, which contribute to smog and respiratory illness again; particulate matter, which contributes to smog, haze, respiratory illnesses, and lung disease; and, of course, carbon dioxide, the primary greenhouse gas produced from the burning of fossil fuels, which plays a significant role in the heating of our atmosphere. Note, we'll talk a lot more about carbon dioxide and climate change in a coming lecture. Together, oil and natural gas provide more than 60% of the energy consumed in the United States in 2016. The energy source mix has changed from past years, and it will change in the future. Current notable trends in the consumption of energy is that we see a rapid increase in both natural gas and renewables, but a steady decline in coal use. So you can see we're still increasing our natural gas use, but coal is declining rapidly. On the contrary, renewables are starting to skyrocket. 25% of petroleum comes from offshore wells, and over 50% is imported. For example, Saudi Arabia, we import 1,166 barrels a day, 842 barrels a day from Mexico, 789 barrels a day from Venezuela, and 364 barrels a day from Iraq. The supply of petroleum, like coal, however, is limited. According to an estimate from BP in 2014, based on reserve estimates of about 1.688 billion barrels, the Earth has enough oil left for only about 53 more years at the current production levels. Granted, BP's estimate relies heavily on proven reserves, so again, we could find more. But that's kind of an alarming, staggering number. 53 years is our lifetime of supply for petroleum. Well, that's possibly in many of our lifetimes that we could see at least a significant shortage of petroleum. So, like coal, petroleum and natural gas are biological products derived from the remains of organisms. However, while coal formed mostly from plant material that accumulated in swampy environments on land, oil and natural gas originated mainly from microscopic marine plankton in ancient seas millions of years ago. This organic material accumulated in marine sedimentary basins with mud, sand, and other sediments that protected it from oxidation. With increased temperature and burial, chemical reactions gradually transformed this organic matter into the liquid and gaseous hydrocarbons that we call petroleum and natural gas. Okay, so there's a lot to discuss on this slide. Unlike the organic matter from which they form, petroleum and natural gas are mobile. These fluids are gradually squeezed from the compacting mud-rich layers from which they originate, called a source rock, into the adjacent permeable beds such as sandstone, where openings between sediment grains are larger. Because this occurs in a marine environment, the rock layers containing the oil and gas become saturated with salt water. Oil and gas, being less dense than water, migrate upward through the water-filled pore spaces of the enclosed rock. A geological environment that allows for the economically significant amounts of oil and gas to accumulate underground is called an oil trap. Several geological features can act as oil traps and have two basic features: a porous, permeable reservoir rock that can yield petroleum and natural gas in sufficient quantities to make drilling worthwhile, and a cap rock, such as shale, that is virtually impenetrable to oil and gas, and hence traps them in their reservoirs. The figure here illustrates the following common oil and natural gas traps. An anticline, which is shown in part A of the figure. This is one of the most simple traps, and it is an up-arched series of sedimentary stratas. The rising oil and gas collect at the top of the fold. Because of its lower density, natural gas collects above the oil. Both rest upon the denser water that saturates the reservoir rock. So you can see that here, gas sits at the top, then oil, and then water because of their densities. The second type, in part B here, is a fault trap. When strata are displaced so that a dipping reservoir rock abuts an impenetrable bed, a fault trap forms. The upward migration of the oil and gas is halted wherever it encounters a fault. So there could be a natural fault in the earth, and so here we just see a reservoir with our gas, oil, and water that gets stuck along this fault. So it's locked in by the cap rock, and it's stuck from moving any further to the left and up because of the fault. The third type is called a salt dome. In the Gulf coastal plain regions of the United States, important accumulations of oil occur and associated with salt domes. Such areas have thick accumulations of sedimentary strata that include layers of rock salt. Salt occurring at great depths has been forced to rise in columns by pressure of overlying beds. These rising salt columns gradually deform the overlaying strata. Because oil and gas migrate to the highest level possible, they accumulate in the upturned sandstone beds adjacent to the salt column. So here's our salt column in the middle, and everything's getting pushed up around it. Well, gas and oil sit right at the top wherever there's an opening because they are the least dense substances in that region. Last but not least is the stratigraphic or pinch-out traps. These result primarily from the original pattern of sedimentation rather than from structural deformation. The stratigraphic trap exists because a sloping bed of sandstone thins out to the point of disappearance. Regardless of the type of trap, when drilling punctures the lid created by the cap rock, the oil and natural gas, which are under great pressure, migrate from the pores that they're in to the reservoir rock and through the drill pipe. On rare occasions, when fluid pressures are great, it may force the oil up the drill hole and cause a gusher at the surface. Usually, however, a pump is required to extract the oil. Okay, at this point, before we get into fracking, I do have a video posted, or a link posted to a video in the description of the YouTube video. So if you would, try to visit that and it'll show you basically a video demonstration of these 4 oil traps. So visit that link, please, when you can. Some shale deposits containing significant reserves of oil and natural gas that cannot naturally leave because of the rock's low permeability. The practice of hydraulic fracturing, often known as fracking, is used to shatter the shale, opening cracks through which the oil and natural gas can flow into wells and can then be brought to the surface. The fracturing of the shale is initiated by pumping fluids into the rock at very high pressures. The fluid is mostly water but also contains other chemicals that aid in fracturing processes. Some of these chemicals may be toxic, and therefore there are concerns about fracking fluids leaking into freshwater aquifers that supply drinking water to people in the region. The injection fluid also includes sand, so once the fracture opens in the shale, the sand grains can keep them propped open and permit the oil and gas to continue to flow. Once the fracturing has been accomplished, the fracking fluid is brought back to the surface. This wastewater is often injected into deep disposal wells underground, and in some locations, these injections can trigger numerous minor earthquakes. For me, recording this video in Oklahoma, and many of my students in Oklahoma, we're familiar with these fairly weak earthquakes. We've seen a significant increase in the number of earthquakes in Oklahoma ever since fracking has started in the state. And again, it's not the process of fracking that creates the earthquakes, it's the water injection afterward that causes it. But regardless, it's still a byproduct of fracking. So due to concerns about potential groundwater contamination and induced seismic activity, this fracking process remains a controversial practice. Its environmental effects remain a focus of continuing research. Okay, at this point, I just added in 2 of my own slides I think that are really important at this point. So the first is the energy demand. The United States Energy Information Administration, or the IEO, its latest International Energy Outlook in 2017 projected that the world energy consumption will grow by 28% between 2015 and 2040. Through 2040, the report projects increased world consumption of marketed energy from all of the fuel sources, except coal, which is projected to remain essentially flat. Renewables are expected to be the fastest growing energy source, with consumption increasing by an average of 2.3% per year between 2015 all the way to 2040. Coming in second is nuclear power at 1.5% per year. So here this just shows over time our world consumption. So note it's different from the United States consumption, right? Different countries use different resources in a variety of ways. So this next picture is going to be very scary looking, but bear with me. There's a lot to see here. So on the left-hand side, we have all these different sources of energy. So solar, nuclear, natural gas, coal, petroleum, and so on. And this chart shows basically the breakdown of where it's going. So petroleum is going mostly to transportation, but partially to industrial, and then just a little bit to residential and commercial uses. So that's what the main thing here is. It's showing what each type of energy resource is being used for each type of, use, whether it's being used for generation of electricity, commercial or residential businesses, industrial uses, or transportation. And then at the end, it shows that there's energy being used, and this is the key point and the main reason I put this here, energy rejected. So let's explain. Many observers have pointed out that the demanding of more energy while also failing to conserve is like demanding more water to fill a bathtub while leaving the drain pipe open. Conservation and efficiency strategies by themselves will not eliminate demands for energy, but they can make demands much easier to meet. Much of the energy we consume is wasted, shown on this chart again by the rejected energy on the top right. Our use of energy is so inefficient that most potential energy in fuel is lost as waste heat, becoming a form of environmental pollution, such as the warm exhaust from automobiles and furnaces. The efficiency of a nation's cars, the light bulbs in factories, determines basically how much waste heat is produced and how much fuel and electricity can be put to productive use. So this chart, again, is basically just showing you that almost 2/3 of the energy that we're using is wasted. It goes back to the environment as heat or contamination. So we're using only about 1/3 of what we actually are producing. The amount of energy wasted through poorly insulated windows and doors alone is about as much energy as the United States receives from the Alaskan pipeline each year. Okay, so at this point, let's go ahead and close out with some questions. So again, you should read these, pause the video, and once you have an answer, think you have an answer, continue to the next slide where the answer is shown. Number 1, the major role of thermal energy or heat in metamorphism is what? Well, in this case, purpose is driving chemical reactions that lead to recrystallization. So as we learned about, heat will trigger chemical reactions that result in the recrystallization of existing minerals and the formation of new ones. Question number 2. Blank is the nearly flat arrangement of mineral grains or structural features within a rock. The answer here is C, foliation. Foliation refers to any nearly flat arrangement of mineral grains or structural features within a rock. Question 3. Which rock is shown here? You can see the pieces down here and some on the rooftop. Okay, here the answer is slate. Slate exhibits excellent rock cleavage, which is why we use it for a lot of walls, rooftops, billiard tables, and so on. Question 4. Metamorphism of limestone will produce what? In this case, it will produce marble. Marble is produced by the metamorphism of limestone or dullstone, which we haven't really brought up. And last but not least, which type of oil trap is shown in this figure? The answer for this question is C. It's a stratigraphic trap. These are the ones that results primarily from the original pattern of sedimentation rather than an actual structural deformation. So that's it for our rock lectures. So I know rocks tend to be more dry material, but I hope you found at least some of it interesting. From this point, we will segue off to discussing the earth processes that involve all of these rocks, starting with plate tectonics, then moving to things like earthquakes and volcanoes down the road. So as always, thanks for watching and have a great day.